degeneracy pressure, which basically means that you can't squeeze electrons together beyond a certain point anymore. So you're kind of like stuck at being of a certain size. And white dwarfs, we got the Chandrasekhar limit. What was it? Quiz question. We saw that the maximum possible mass for a white dwarf, it's called the Chandrasekhar mass. And it comes out to be something like 1.4 solar masses. Squeeze electrons, you get boom. So no, that does not happen from squeezing electrons. What you're talking about is the atomic bomb actually works with nuclear, it's actually a nuclear fission. Nothing to do with electrons. It has to do with the nucleus of the atom of heavier elements like the uranium. And it has to do with breaking apart a nucleus. Nothing to do with the electrons. So, spreading misinformation in my chat here. Not allowed. So, next we will talk about neutron stars, just to recap. What happens to stars whose initial mass is greater than 7 solar masses? There aren't many stars that massive, but they do exist. Very massive stars have short lives and die spectacularly, leaving behind a badly crushed corpse. The main sequence lifetime of a massive star is short. So we were just talking about the main sequence being long, but if you're a very massive star, you're going to spend shorter time on that main sequence. Life after the main sequence, when the star becomes a supergiant, is even shorter. The ultra-luminous supergiant is relying on less efficient energy sources. Fusing hydrogen to helium releases about 6.4 times 10 to the 14 joules per kilogram. Thereafter, fusing helium all the way to iron releases only 24% as much energy per kilogram. So we kind of saw all of that. We talked about Betelgeuse, who is expected to supernova any moment now. And then we talked about how the neutron stars, which is what we get as a stellar remnant for these higher mass stars, are supported by neutron degeneracy pressure. So core collapse can be stopped by neutron degeneracy pressure, because remember, there's a core collapse, that neutron star forms. Degenerate non-relativistic and electrons have a pressure. The Fermi exclusion principle applies to neutrons as well as to electrons. Degenerate non-relativistic neutrons thus have a pressure as well. And a sphere of neutrons supported by degenerate neutron pressure is called a neutron star. You two are clearly the same person with two accounts. Oh, okay. Okay, so a white dwarf, oh yeah, and we also talked about how a neutron star radius is around 10 kilometers, 11 kilometers, something like that. So really pretty tiny. A neutron star is often compared to the size of Manhattan. It's very tiny compared to, its mass, and especially compared to the mass of the star and the size of the star that it might have come from. So all of that recap about the neutron stars. Ooh, and we also talked in much more detail about pulsars and how neutron stars are associated with pulsars. Pulsars are associated with neutron stars. And also pulsars are associated with core collapse, which is what leads to neutron stars. And core collapse, of course, happens to those very massive stars. So all of that we talked about a couple of lives ago, maybe the last live. And now, finally, after all of that, we come to black holes. Okay, so we will just touch upon this, because why not? We're here. So neutron stars are not the ultimate in compression for stellar remnants. We saw how there is, aren't you in the... Oh wow, look at you, Reese, you're famous. People know you.